So our next talk is by Chun-Kit Lai from San Francisco State University, and I will be the moderator for that talk. And Chun-Kit's talk is titled Fourier Bases and Fourier Frames for Singular Measures. So Chun-Kit, when you're ready.
Okay. Yeah. First, thank you very much, particularly for Josh and Mandapika to invite me to speak in the PRIM conference, and hope everyone is healthy and safe. And so my talk today will be on Fourier basis and Fourier frame. Well, let's mention some of the background. Well, we'll start with a kind of abstract setting on the Hilbert space. So if we have a collection of vectors in the Hilbert space, I call it is a frame. So what it means is that I can find an absolute constant A and B so that you have a generalized polytope identity. So that means you turn it into equivalence instead of identity. So let's also set up some of the terminologies. So if we just have the upper bound, so the set will be called a Bessel sequence rather than a frame. Well, it may happen that A is equal to B, then you have equality. In that time, it will be called a type frame. And if you are even better, A equals B equals 1, then you have Parseval identity, so it will be called Parseval frame. But Parseval frame may not be orthonormal basis, because you may imagine you have two orthonormal bases, add together, it will become a two-type frame, but then you normalize, so it will become a Parseval frame. So an orthonormal basis will be a Parseval frame together with orthogonality. So, and finally, a frame is complete because if you see the lower bound, it is complete, but it may be over complete. So just like linear dependent set, it may be, it may not be independent. You have non-unique expansion. So in the case you become unique, you have a unique expansion. At that time, you will be called Ritz basis. So these are the terminologies for the frame theory, and frame theory is used in a lot in the signal processing. And the main dish today for us to do is not on general Hilbert space, but on the L2 mu space. And the frame we are considering is the exponential frame, which is E2 pi I lambda x for some frequency set lambda. And given me a Borel probability measure, a set E lambda is called Fourier frame. You have a frame inequality there. And if such thing exists, then it will be called frame-spectral measure, and the lambda will be called frame spectrum. And similarly, we have defined type frame or Ritz basis, and in particular orthonormal basis. If you have orthonormal basis for this exponential mu, it will be called a spectral measure. So the classical result is that in classical Fourier analysis, everyone knows is the characteristic function of the unit group with a spectral measure, because they are you have a mutually orthogonal basis using integer as frequencies. So so in that case, this set, the unit groups, is also called a spectral set. So so let's mention about the history. So the first one who studied spectral measures or spectral set in classical setting was Fourier. So in 1974, Fourier proposed a conjecture. So what kind of set out of other than the unit group can be a spectral set? You admit an exponential basis. So he made a conjecture. Omega is a spectral set if and only if omega is a translational tile. You can tile by translation to cover the whole space of RD. So this conjecture was told by Alex Yusovich before 2004. Everyone believed the conjecture was true, but in 2004, Terry Tao gave the first counterexample of this conjecture in dimension 5, which certified the death of this conjecture. So, and later on, this conjecture was modified by other people. This conjecture was not correct in dimension 3 or above in both directions. Well, up till now, today, this conjecture is still open on dimension 1 and 2. And although this conjecture is false, the mysterious relationship between spectral set and this tiling, on one side is kind of a number theoretic thing, on the other side is Fourier analytic, has a lot of mysterious relationship, and there's a lot of research questions, and not many people completely classify or understand the exact relationship between them. So let's mention some of the recent progress concerning just the Fourier conjecture. Well, the conjecture, although it's false, it is still true in the setting of convex set by Lai and Matoshi last year. Essentially, if you have a convex spectral set, well, it must be a polytope, convex polytope that tiles by translation. And on the other hand, the conjecture can also be asked in other abelian groups, discrete abelian groups. Well, actually, most of it is true. For kind of low dimensional groups or cyclic groups, they are basically, the conjecture is true. And in particular, one remark we can do is if you want to prove the conjecture for dimension 1, if you are able to prove the conjecture in all finite cyclic group in dimension 1, you can prove the Fourier conjecture in dimension 1. Well, to make it a more general thing is orthonormal basis, everyone believes it is very, very rigid because of orthogonality. So people ask for rich spaces, which is a little bit more general. You don't need orthogonality, but you still have frame and unique expansion. So this becomes a rather hard question. And in particular, just simple stuff, just like the ball or triangle, whether you miss rich spaces, Fourier rich spaces is still an open question. So ball doesn't tile, and triangle, you need rotation to tile, but we are not allowed to have rotation, and they are known to have no orthonormal basis. They are not spectral set. So this is a very hard open question. We are in the field. So well, my talk today is not just on the classical case. We are on the fractal case, a singular measure. And well, we may expect how come a singular measure could have an exponential basis. Well, indeed, this is true. Jorgensen and Peterson was the first one to find that, well, there is singular measure with their spectral measure. They have exponential orthonormal basis. Well, the set is the self-similar measure supported of middle fourth Cantor sets. So that means you divide your interval into 4 pieces and just choose 2 pieces. Actually, any 2 pieces works. Here they use a 2, 0, and 2. So that measure is the Hausdorff measure supported on the Cantor sets, or is a self-similar measure, or what we use is an infinite convolution of Dirac measure of 2 points, and then convolution the next level 4 points and the 8 points continue. So this measure, what Jorgensen and Peterson find is that, well, the middle fourth Cantor set with this measure is a spectral measure, and the spectrum is a sparse spectrum with is the Fourier expansion with digits 0, 1, all the frequency. So so this was the major advance. This side is a spectral measure, and well, one may actually ask, how about the middle third? So how about the middle third? Is a spectral measure? Well, in the same paper, they find it. Well, the middle third one is not a spectral measure, so that indeed, they are very far away from orthogonal. If you try to count how many orthogonal exponential they have only 2. So that means you have at most 2 mutually orthogonal sets. So, so the same things also happen. If you are doing even contraction ratio, they are spectral measure. If you do odd contraction ratio, they are never spectral measure. Well, this is the picture of Jorgensen and Peterson, who mixing the spectral measure theory into the singular measure. So, so they are not spectral. And one of the major questions first asked by Strickert was that is the middle third Cantor measure a means of Fourier frame or rich spaces? So it's still open up to today. Well, maybe let's ask something more broader. How about any singular measure? Would they have Fourier frame? So other singular measures, would they have singular frame, Fourier frame, but they are not yet spectral? Or can we have some ways to determine some measure of spectral or not spectral, or frame spectral or not frame spectral? So these are the main theme of the question, overarching question I would like to answer, or I would like to give some progress today. And well, some of the application for it is Fourier frame in the signal processing point of view is kind of the signal transmission and stable reconstruction of the signals. So from the dual side, it's called the Paley-Wiener space. And in some sense, if you try, we are trying to kind of reconstruct stably. If you have a Fourier frame, you are trying to reconstruct the signal stably, whose Fourier frequency is supported on certain sets. And you may imagine you are supported very close to a Cantor set. And you try to reconstruct a signal whose frequencies support very close to a middle third. Can we construct stably in some sense, uniformly stable until the end? So that's kind of the intuition if you're trying to think of it in the Fourier side. So so that means the question is, what kind of measure will be a Fourier frame? So so that's one of my results with He and Lau. Lau was my picture advisor. And so first of all, if you want a measure to meet the Fourier frame, it must be so-called a pure type frame, pure type measure. Pure type measure.
So one quick question for you, Chun-Kit. We had a question to repeat the definition of a Fourier frame, just so it's fresh in the audience's mind.
Okay. Yes. So let's go back to the. So a Fourier frame. So you get a countable set of exponentials, and so that if it is if satisfy a generalized partial identity, so that means you get a constant. The L2 norm is equivalent to the inner product of F with respect to the E lambda. So, and if it's a spectral measure, it means you have missed an exponential basis. Does it answer the question? Yeah. Okay, so let's come back to the major questions. So yeah, what we are asking is what kind of measure will have a Fourier frame? So this is a pretty broad question. Let's try to pin it down into some kind of category. So first of all, it's in 2013, we have the first result. First of all, if you want a measure to have a Fourier frame, it couldn't be mixed type. So it must be purely discrete, it's a Dirac measure, or purely absolutely continuous or purely singular with respect to the back measure. So it's kind of expected. So that means if you want to do some classification, maybe, so we can do it in the three classes. So indeed, the first class for discrete measure, actually everything, if you write it down the definition, everything goes back to linear algebra. And just playing around with linear algebra, you can actually classify everything. Basically everything, not just frame-spectral, they are mid-risk spaces. And well, let's go to absolutely continuous measure. Well, actually, so as we talk about Fugili conjecture, for orthogonal bases are kind of difficult, but actually Fourier frame for bounded set are pretty easy. Well, you can imagine if you have a bounded set, whatever, very ugly shape, you find a square covered, and the square has orthonormal bases. And if you, so you have pointer identity, and then you restrict it to the set, you immediately obtain a type frame. So the frame constant may be very bad. By certain normalization may be very bad, and but it is the frame. So well, bounded set is easy. So how about unbounded set of finite measure? This one will become much difficult because you don't have a square covering. So well, it was eventually answered by Lisan, Olipsky, and Ulanovsky. Well, what they use is a Cartesian-Singer. They kind of control the frame bounds using the Cartesian-Singer. And later on, I will give you some kind of explanation on this thing. So,
sorry to interrupt one more time, just to make sure our whole audience isn't getting, that no one's getting dropped. If we could pop back to that definition one more time, there's a bit of confusion whether the index I is playing a different role in different slides.
Sorry. So let's,
or actually, maybe Ajit, if you could unmute for a moment and ask your question to make sure I've portrayed it properly.
Yes. So
Ajit, is it possible for you to unmute your mic and ask?
okay. So I think maybe there's a little bit of typo here. Maybe sorry about that. So I think in the definition you are summing up all the lambdas. I forgot to So this should be sum all the lambda in lambda. So I forgot the index I. So here is the, maybe is the confusion comes from, maybe.
Got it. Okay.
Yeah.
I think
so you're
that,
summing up all the lambdas. So yeah, thanks
perfect.
for correction.
Okay, thank you very much.
So I think I see another question is this a theorem also valid to integrability? I don't know what is integrability. Maybe we can discuss it later on. Yeah.
Sounds perfect.
Yeah. So yeah, for the absolutely continuous case. So so can we classify? Indeed, we can also classify it. This is kind of related to uniformity of the measure. If you want a GX to have a Fourier frame, so actually we can classify in terms of density. The density, it must be essentially bounded. So it's in L infinity, and actually 1/G is also in L infinity. So there's a bound above and below, away from zero almost everywhere on the support. So this part, I will give you a proof if we have time in the later section. So so in the rest of the talk, I will try to do this the same several progress we have done so far. So first of all, we will generalize the Jorgensen-Peterson construction, and we can find some of the Fourier Cantor set with Fourier frames. And then the second part will be the uniformity. We can actually find a uniformity, kind of looks like house of measure as kind of a important necessary condition for a measure to have made a Fourier frame. And finally, surface measure, instead of studying just on the Cantor measure, actually we have some result on the surface measure, just like the unit sphere, the surface of the unit sphere. So are they frame spectral? So that's what I'm going to plan to go through. So so let's study about the frame spectral measure on the Cantor type construction. So for the easiest way to understand it is go back to the Jorgensen-Peterson example to see why it works. So we remember the contraction ratio of middle four is 1/4. So I write in the expanding way is 1/4. And we are choosing the digit 0, 2. And if you look at this one with L is 0, 1, and then I form a matrix. So the the spatial variable is 0, 2, and then the frequency is 0, 1. And then you try to compute the kind of Fourier matrix. It is actually a Hadamard matrix, which means it's orthogonal. The rows are mutually orthogonal, and actually the column as well. So so that if you interpret it in the Cantor set, that means the first 2 points of the Cantor measure, the Cantor measure is the infinite convolution of discrete measure, and then the first level is actually spectral measure. It's a discrete point spectral measure. And well, the interesting point here is that I can iterate the same stuff. You go down to the nth level, and because everything we do are integers, so this is the key point. Things works out nicely, and in the nth level, and you iterate the spectrum into up to nth level, they are all spectral measure. And what it means that you have you form an unitary matrix. So that means the first nth level convolution, they are all spectral measure. So if you write it the partial identity, that means yeah, you are summing up to nth level, just the first n of them. Yeah, actually you get to the power n elements, and the nth levels discrete measure, they have partial identity, and it works for the characteristic function. So for analysis, that means next step will be take the limit, because mu n converge weakly to mu. So if you take n goes to infinity, the right hand side will go to what you want, but the left hand side is a bit tricky, because this is just discrete measure and your number of elements is increasing. So this part become tricky. So the part that is missing is the tail point, the tail measure. So in order to really go through to pass the limit, there is a kind of a little bit technical condition, which is I don't want my tail measure on the spectrum on the first nth level to be too small. Well, this condition can be satisfied, and after that, we can conclude mu4 will be the spectral measure. So so that means the scheme we are doing is, okay, we first find all nth level, they are good spectral measure. And then we have a little bit technical condition. And this technical condition could, indeed, is not a very big problem. For most of the time can be satisfied. And I have a lot of theory about how to remove this condition. And then we'll be able to conclude the final ultimate measure will be spectral. So, so in order to produce a frame, so we, instead of doing Hadamard matrix, which every time is mutually orthogonal, we need to change it to so-called frame tower. So now I'm doing different scale. So Nj will be the contraction ratio, and Bj will be some integers. So each Nj will, the contraction ratio is at least 2. So if you have a frame tower, and then we have kind of an error estimate called epsilon j, which is summation finite. So if you have this is a frame tower, if first of all, Nj are all integers. Secondly, the Bj are the subset of integers chosen from 0 to Nj minus 1. And for simplicity, we assume 0 is always inside. And then finally, this is the generalization from the Hadamard matrix, the orthogonality relation. So I can find another subset of integers so that I form the matrix. And then the matrix norm is almost orthogonal. You can imagine is just 1 minus epsilon j and 1 plus epsilon j. So previously orthogonal is always equal. Now you allow a little bit of perturbation. So they are no longer orthogonal, but they are still looks like very close to orthogonal. So I need the epsilon j. So we do it in the same way. Well, previously is 0, 0, 2, and then keep convolution, do the convolution. Now I do 1 over n1. So new one is b over n1. And so the first level divide into n1 and then choose b of them, choose the b. And then second level, I go to 1 over n1 scale and then divide into 1 over n2 and then choose b2. And then horizontally, they have to be the same so that I can preserve the convolution structure. And then, well, in particular, when is it still similar, is if I do everything is the same, and then the Bj are always the same, just like the previous 0, 2, the middle 4, or 4, and then the B are always 0, 2, they will become self-similar. So here, every level may be different. So, well, if we produce a frame tower, so I can kind of iterate the same thing. So the nth level measure, I iterate the L1s. Okay, this is the typo. This n minus 1 should be down. Should be down. So I produce an n minus 1, and then we have the Fourier proposition, which is saying that okay, up to the nth level convolution still a discrete measure. They are frame-spectral, and then the frame bound is important. Now the frame bound will accumulate by a product of 1 plus epsilon j, and the lower frame bound is 1 minus epsilon j in the product. So previously all are 1. Now you get a little bit of increase, but I well control the increase because summation epsilon j is finite. So this if we take the product up to infinity, it will not have a problem. It's still a finite upper frame bound and finite lower frame bound. So that's the result. And then there's a slightly technical condition. And when assume the technical condition and the canonical spectrum by using the Ln will become a frame spectrum. And the frame bound will be pushing it to infinity. So that was the result. So you may ask, oh, do we have any frame tower? So do we really have a frame tower or just hypothetical? I imagine I have a frame tower and then do a theorem. So indeed it exists. So the way we do it is that, so we have, it's still almost like a tiling. So we do the Bj is is in a arithmetic progression, and the Lj is arithmetic progression. And the contraction ratio, I product a little bit with the alpha j. So if we imagine if alpha j are all zero, the nj, bj, and lj, you form the matrix, will be mutually orthogonal. You become back the Fourier matrix because the mj, the kj will be cancelled out. So now I kind of, the alpha j destroyed the orthogonality structure, but I can still preserve the frame tower structure. So that means it's no longer orthogonal. If in the presence of this alpha j, it's no longer orthogonal. But if we assume the summation of this is finite, I can make a frame tower. And then the measure will not be spectral. For some of the measures will not be spectral. So so that means the frame tower construction does exist in some cases. And well, just go back to the question about the middle third. Well, if we want to use the approach to construct a Fourier frame using the frame tower construction, one of the main idea is to construct a frame tower. So the frame tower here. So, but certainly if you do the middle third, if you just do the 2 digits is too small. It doesn't work. So, but the convolution structure is interesting in the way that, okay, I can make more. I can make the first nth level. Then you have a 2 to the power n matrix. So, and then in the next level, you can do even longer, 2 to the power n1, and then in the next block 2 to the power n2, 2 to the power n3. So when you block it, it becomes larger and larger. So actually the frame tower construction can be reformulated in the following idea, which is, okay, give me epsilon. I can find n. So you go down deep enough to some of the levels, and then some of the ln in the c to 3 to the power n. So the bn is the Cantor measure in the nth level, and then so that this matrix is almost orthogonal in the following sense. So you've given me an epsilon, I can always do such thing. I can go down to the level and then find some very almost like orthogonal Fourier submatrix. Then I will be able to construct a Fourier frame. So there's a technical condition, and I check the technical condition basically is you don't need to worry about it. So but if we go to finite level, we can make it almost like mutual orthogonal up to at certain level. I will be able to win the game. So let's look at it carefully. So instead of choosing Ln, well, what if I choose everything? So if I choose everything, it's actually so-called tight frame. It's a tight frame, and the tight frame constant is pretty big. It's 3 to the power n over 2 to the power n. So so it's still very far. It's very far away from the 1 plus epsilon and 1 minus epsilon. So if I choose everything, it's still very far away. Well, but it reminds us the Cartesian-Singer. So let's talk about the Cartesian-Singer. So Cartesian-Singer originally was a conjecture by Cartesian-Singer in the setting of Neumann algebra, but later on they refined it into many equivalent conditions, and one of the conditions is related to frames. And before these three guys gave a proof, people generally believe the Cartesian-Singer was false, but to the surprise of many people, this turns out to be true, and they make the proof. And let's kind of study the version they proved in terms of frame theory. So the idea is, okay, I have R, which is a positive integers, and then I have kind of some vectors, and they form a partial frame. So this M may be very large, and just go back to the previous case. It's kind of you do a normalization, so you normalize the 3 power n over 2 to the power n to the other side, so that this becomes 3 to the power n, and this become 1. So now the vector become very small. The length of the vector become very small. It's no longer unit vector. It becomes very small, and in our case, it's 2 to the power is 2/3 to power n. So the theorem says that I can partition my set, partition this very hugely redundant type frame into R partition. So this R into R partition, so that each of them is kind of roughly decomposed, roughly of the same frame bound. So imagine the delta is imagine if there's no delta, if don't see a delta, it's 1/R. So it's 1 to 1/R. So you almost like you do a very good partition, and every partition, the frame bound is kind of the same thing. It's kind of the same numbers. So but here, of course, you are missing the lower frame bound. You are missing the lower frame bound. So to get a little bit of improvement, this proportion due to Nissan, Olivsky, and Rolanowski, when they do an unbounded set, is that I can iterate. So in some sense, I iterate this theorem in the case of Fourier matrix. Then I can find some universal constant, and such that independent of n. For all n, I can always find some Jn, so that it forms a frame, and with these two universal constants. So these two constants is independent of n. So imagine you almost like you can take limit, but the major problem here is that this Jn is very sparse. So you cannot really take a limit, because if you take a limit, as n goes large, the Jn is getting sparser and sparser. In the end, you may not have a good distribution of Jn. You don't find anything. But this is not the case for a set of positive Labbe measure, and this is why they can prove the exponential frame exists for unbounded set. So because for set with positive Labbe measure, the Jn will not be too sparse, and they can kind of take the limit to control the distribution. But in fractal case, there's no such game. And but if you do the frame tower construction, if I can make it, so what I still a little bit far away is we need the C0 to the capital C0 instead of a universal constant. I want, if I can make it into as small as you want, as n goes down, then I will be able to construct a Fourier frame for Cantor measure. So this part is also related to factor uncertainty principle by Diatov and Jean, in the sense that if you have read the paper, they actually, for the middle third Cantor measure, they can actually try to quantify so-called uncertainty exponent of the delta. And in some sense, if we can construct a Fourier frame, I checked that is kind of related. The uncertainty exponent is maximized. You get to the maximum uncertainty exponent. And in their paper, they also found that if you have a Hadamard matrix, the uncertainty exponent is maximized. So that's another thing that is kind of very related to the fractal uncertainty principle. So that's about the fractal measures results. So another so let's continue to another kind of important properties for frame-spectral measure, which is called uniformity. So here I will need a definition, which is called translationally absolutely continuous. So we say that measure mu is translationally absolutely continuous. So if you have a support mu, and then I fix the set E, and then you fix a translation E plus T. So, and the assumption is that I have a E and I have a E plus T. They are all in the support. They are inside the support of mu. And then I want to translate E to E plus T. So first of all, I have a measure mu on here. So which is a mu restrict on E, which is the mu measure. But on the other hand, I consider another measure, which is called omega, which is measuring E plus T and F plus intercept F plus T. So that means you move the set F to E plus T. Well, but you are still measuring the things here. So imagine this is just like, so in US, we measure length in miles. And then I measure length in calendar using kilometers. And now I kind of bring back my measure in calendar to US. So that means I measure my length in US using kilometers now. So that means omega is bring back the kilometer measure to US. And now the assumption is that, well, if I bring back laterally, the miles and kilometer are absolutely continuous with respect to each other. So my assumption of translation absolute continuity means that if I bring back the measure from the other side to my place we are measuring, they're absolutely continuous to each other. So that's the definition of translationally absolutely continuous. So so that was the result we proved in myself with Doreen Decay in 2014. So if I have a frame spectral measure, if there is a frame and with certain frame bound, and then I have a translation absolutely continuous holds on certain set E. So then that means I have the random Euclidean derivative. So the random Euclidean derivative will be bounded above by the frame bounds B over A, and then bounded below by A over B. So that was a this result is kind of manipulating the frame inequality and use the absolute continuity. So we restrict the function to the characteristic function of E, and then move it to the other side and then bring it back. So after certain calculation, we will get this. So so this result is kind of it makes a lot of new progress about Fourier frame in particular. So if you consider self-similar measure, so this is the middle fourth. Instead of equal weight, 1/2 going down, I do P 1 minus P, P 1 minus P, P 1 minus P. Every time I go different. So in that case, this self-similar measure would not have Fourier frame. So if P is not 1/2, it's not equal weight. So the reason is that if you are in the nth level, the left-hand side, the measure will be P to power n. The right-hand side will be 1 minus P to power n. And if you try to calculate the random Euclidean derivative between these two, the two extreme pieces, the two extreme pieces, the random, they are absolutely continuous to each other. And then the derivative will be P over 1 minus P raised to power n. And then I want P over 1 minus P raised to power n to be bounded above and below. The only possibility is P is 1/2. Yeah. Otherwise, they will not be equal weight. Otherwise, they will blow up. Either side will blow up. So that gives you the first proof that, okay, some measure will not have Fourier frame if they are not uniform enough. So this also provides another kind of interesting proof about the absolute continuous measure, because if you have a absolutely continuous measure, which is frame spectral, now I consider the upper bound as the density that is slightly below the upper bound and slightly above the upper bound. And then if these two sets has a positive measure, you can use convolution. So that's kind of like a qualifying exam question is I can always find a set of positive Lambda measure to move from C epsilon to D epsilon. So to move it from here to here. So, and then I can check the translation absolute continuity on this set. So I can move it from here to here, and then I check. When I check it, so the density on the E is G. But if you move it to D epsilon, it will be G plus T, Gx plus T. So that's the density will be the difference. And now, because I assume you have a frame, so you have the previous result. The density is bounded above and below, and the density is just like this. Is at most this one. So is on this is the bounds. So and take epsilon to 0. So we get an essential sup and essential inf is bounded below and above by the frame bounds. So that what does it mean is this provide the proof of the characterization of absolutely continuous measure. So the Gx must be uniformly upper bound and bound away from 0. And it actually says a little bit more. If I make it to spectral measure, A equals B, or you admit a tight frame, A equals B. So sup and inf has to be equal. It has to be a constant density in order to admit a tight frame or a spectral or an orthonormal basis. So that means if the measure has certain density that is non-constant, you would not expect to have any orthonormal basis. So that's the other application. So and in general, what it means is that if you have a frame spectral measure, the density of kind of, it looks like it should be very uniform. The measure has to be very uniform on the support. So there was a kind of conjecture at that time we tried to say I can remove the absolute continuity. Actually, it must be a necessary condition, and then the set has only one so-called local dimension, so it would not have different dimensions, and it must be translation absolutely continuous. So that was a conjecture that time, and later on, first of all, the first part is still an open question, but the second part is not quite yet true. So one local dimension, there is a way to get rid of it. It was by Leonave in 2016. So what he considered was that, okay, I consider frame spectral measure on the plane. On the other hand, I add another measure on the z-axis. So they are kind of orthogonal in independent direction of each other. And he showed that, well, if mu and nu has no atoms, it's not purely discrete, the addition will be a frame spectral measure. So so that means it kind of say you still have two local dimensions in two independent directions. But it still doesn't quite answer translation absolute continuity. The reason is that there is nothing you can translate from the z-axis to the plane except one point, except a point. The only thing you can translate from the z-axis to the plane is one point, and then the one point has zero measure because of his assumption. It has zero measure, so that means you cannot. The translation absolute continuity is still holds because it holds with there's nothing to be checked. So so that's a good way to understand. So translational singular and translation absolute continuous. So, well, if you think translation singular, actually there's some easy way to produce translationally singular measures. So indeed, one of them is, okay, if I do the mu 1/4, and then another I do mu/16. So this picture is a bit ugly. So mu4 and then 1/16. So the support of mu1/16 is just a subset of mu4. And then I add them together. So this part has positive measure, but if I translate it into the mu4, you become zero measure. So that will be singular. So you have a set of positive measure, but after your translation, it becomes singular. So that's actually the simplest example of translational singular measures. And
yes. Sorry to interrupt. There was a nice question here. Someone was asking, which properties of non-atomic measures do you use at this point?
Okay. Yeah, that's a nice question. So, sorry. So actually what he used is that, so if you are atomic, the measure has only finitely the spectrum is finite dimensional. The spectrum is finite dimensional. So they have, so in his proof, what he needs is you need to be infinite dimensional so that you have many points, many spectrum to choose to build up the measure, the spectrum in the second dimension. So if it has only finite many, then the proof will break down. So yeah. So so this is the first example of translational singular measure, which is easy to construct. And so in 2018, we proved that this doesn't emit any Fourier frame. And of course, this kind of observation can be generalized to something more general. And this specific example does not have any Fourier frame. And how about translational absolute continuous? So for continuous measure, so one of the easiest example of this is all the Hausdorff measures supported on certain set K. So because Hausdorff measure is translationally invariant, so it must be translationally absolutely continuous. So that means ask the question is, so if is now uniform, just like this measure is uniform. Do we have a Fourier frame? Must it have a Fourier frame? So middle third is one of them, but middle third is still unknown. So can we just construct a measure that does not have a Fourier frame or such thing? So that was a recent result by myself, Yusovich, New, and Wyman. Well, as long as you have a convex body with smooth positive, everywhere positive Gaussian curvature and consider surface, they don't have a Fourier frame. So that was the recent result. So the surface of the sphere has no Fourier frame. So the singular measure on the surface. Well, in contrast to this positive curvature stuff, we also consider polytopes. So I consider surface measure on all the polytopes we consider, and we find that all of such thing has a Fourier frame. So that means curvature is kind of an enemy to the Fourier frame now. So so that was another result that we recently produced. And so I still have a little bit of time. I can kind of sketch why this holds. This was kind of amazing proof. Yeah, and so we consider two abstract conditions. So first of all, if you have a frame, a finite Fourier measure, and you have a frame lower bound, you have a lower bound, and then at this moment, I assume you have a Fourier decay. Well, in that case, if I try to sum up all the lambdas raised to the decay, it will be infinity. So that's the first part of the condition. So it's kind of expected. Of course, the proof is need a little bit of estimates. So you may imagine you decays, but you still need a Fourier frame. You still need a Fourier frame. So kind of you need to squeeze it into certain density. So you have another thing to quantify is covariant dimension, but I'm not going to talk about it today. So you have to be summation to be infinite. So everyone knows surface measure of spheres has a Fourier decay of d minus 1. So that means if you sum up to d minus 1, it must be infinity. So, but if you consider Cantor measure, this will be false. You don't have Fourier decay for Cantor measure. There's no Fourier decay. Actually, you can actually construct everything is finite. You can be as expressed as you want. So another property is that if I have an upper bound, the Bessel sequence is kind of like a local expansion. You integrate your Fourier transform locally and then try to erase out your decay. Then you have a lower bound. Then in that case, your sum will be finite. Well, this is a little bit, would you hold? Well, the surface measure also holds. The reason is that if you go back to the asymptotics of the surface measure, well, just the imagination. So your decay term, so move to the other side. You move your decay term to the other side. So it's essentially just a cosine. So, and this lower order term, you can forget it. So that means you are just integrating a cosine. And then if you integrate a cosine a little bit large enough, so actually cosine square. So you integrate a cosine square must have a universal lower bound. So that's the other way. So because the surface measure satisfies both conditions, so that means you got a contradiction. One is finite, one is infinite. So there's no Fourier frame. So that was the kind of the idea of the proof. So yeah, I plan my time very well. It's now 49, so I think it's a good time to stop here. Thank you very much.